if we start with some amount of reactants or some amount of products, that a system will achieve equilibrium. It will achieve some relationship between products and reactants. Let's go ahead and look at what happens to equilibrium when we apply different stresses. How does a system respond? How does it get back to equilibrium? What does it have to do? What changes will it undergo? So what we're looking at is Le Chatelier. Le Chatelier's principle tells us that if we have a system that's at equilibrium, and then you apply a stress, so you're no longer at equilibrium, that system will rearrange to get back to equilibrium. So a metaphor for that, for me, would be traffic in Seattle. So here's Seattle, here's the east side, the suburbs. A lot of people live here, commute to over here. A lot of people do the opposite. So there's always going to be this balance between traffic on 520 versus I-90. 520 ends up always taking a little bit longer than 90. So their equilibrium, let's say that it takes 10% longer to cross 520 than it does to cross 90. So that's the equilibrium. The stress that we could apply to the system would be if there was a game at UW. So now all of a sudden all these people are taking 520, we're adding all this extra to this side. The system's going to have to undo its stress, and that happens by people checking the traffic and saying, whoa, I'm going to avoid this, I'm taking 90, even though it's a longer route for me. So the system undoes the stress by people who regularly take this road would now end up taking this road. So in a chemical system, the way we measure equilibrium is we know we have our K, and that's just the products, so hydronium, over our reactants, let's see, there's acetate, over acetic acid. So equilibrium is always going to be some value of the products over the reactants raised to their coefficients. And I leave water out because it's a liquid. The concentration basically doesn't change. So I can see what happens to equilibrium when I apply a stress. A stress I could apply would be, let's add some hydronium. If I add hydronium, this value is larger. So originally I was at equilibrium, but now I have a bigger number here. So when I'm questioning, am I at equilibrium? Well, no, I have a new value. And since this fraction is now larger, the question of am I at equilibrium tells me, no, Q is too big. Q is greater than K. So to get back to equilibrium, I have to lose some of these products, minus X and minus X, and they'll turn into reactants. So what I'm doing there is I'm shifting left. I'm shifting from the products to the reactants. Let's look at another. What if I added some sodium hydroxide? Sodium hydroxide reacts with the hydronium. So if I add sodium hydroxide, I'm really removing hydronium from the system. So I add my hydroxide to a system that's at equilibrium, and I ask, am I still at equilibrium? No, because this number got smaller. And if this is smaller, when I calculate Q, products over reactants, I can see in this case, Q is less than K. So now, since Q is too small, I don't have enough products. So I'm going to have to shift right. I'm going to shift from my reactants to my products, meaning I lose some reactants and I make more products. So let's look at some stresses we can apply. Here's my system. Nitrogen and hydrogen react to make ammonia. They're all gases, so they'll all be part of the K expression. So that'll be the ammonia raised to its coefficient over the nitrogen and the hydrogen cubed. So that's my K expression. I look at this and I see that there's a change of enthalpy. It's negative. Since it's negative, this is exothermic. All right, so heat is being produced. Heat is a product. I'm going to go ahead and write it in there to make it easier for myself. So let's go ahead and apply a stress. Let's add some ammonia. So if I add ammonia, and I originally have the system that's at equilibrium, it's at K, and then I make this value larger, and I check to see, am I at equilibrium? Well, no, because this is bigger now. So when I question, and I calculate my Q by plugging in the new number, now Q is too big, it's bigger than K. If Q is too big, I have too many products, so I'm going to have to shift left. Some of my products are turning into reactants. So that's losing 2x here, because for every 2 moles of this that I lose, I make 3 moles here and 1 coefficients of 1, 3, and 2. Okay, so that would happen until I got back to equaling K. So the concentration of ammonia would have to decrease, and the concentrations of nitrogen and hydrogen would increase to get me back to equilibrium. So now I'm going to remove some ammonia. And so when I remove ammonia, I can see that the opposite's going to happen. Because now when I have my equilibrium values, I take out some ammonia, and then I ask, am I at equilibrium? No. Because when I plug into my Q, my values into my Q expression, I now have a Q that's going to be too small because I subtracted. So now Q is less than K. I don't have enough products, so now I'm going to shift right. I'm going to turn some reactants into products to get back to equilibrium. So some of those reactants are going to react and become products. So next we have, what if we add inert helium? Well, I have my K expression, and I can see that helium isn't part of that at all. So if I add helium, I don't change any of these concentrations, so nothing. Nothing happens when you add something that won't react with any of your reactants or products. Now for temperature, I've been keeping K the same as I talked about shifting left and right up here, but now I know that K changes because K is constant unless you change the temperature. Okay, so as I add heat, I'm increasing the temperature, and I'm adding to the product side. And as I add to the product side, this side is too big, I'm going to have to shift left. Okay, so this is going to be a shift left. I'm shifting left to reestablish equilibrium, so some of the products turn into reactants. And since I'm losing products and I'm gaining reactants, I know that K is going to decrease. So this is true for any exothermic reaction. As you increase the temperature, you decrease the K. Now let's look at volume. So my favorite K to choose, let's choose a temperature where K equals 1. That's awfully convenient. And for this one, I'm going to say that I have a 1 liter vessel, and that means I'm going to have 1 mole. 1 mole of each substance at 1 liter. So this would be 1 molar, 1 squared, and each of these would be 1. So 1 times 1 cubed. All right, so this side is equal to 1. I'm at equilibrium. So I've got this system at equilibrium, and then I'm going to decrease the volume. I'm going to decrease the volume so that I have a half of a liter. And I still have that 1 mole until I reestablish equilibrium. So if I have 1 mole and half a liter, I now have 2 molar values for everything. So I've got 2 squared over 2 times 2 cubed is 8. All right, so I have 1/4. When I'm questioning with this new change, now that I've applied the stress, I need to solve for Q, and I question, am I at equilibrium? Well, no. K was 1. My new values, when plugged into that K or Q expression, give me 1/4. Q is too small. So I can see that Q is less than K. I don't have enough products, so I'm going to have to shift right. And this makes sense without using the math as well, because I have 4 moles of gas in the reactants, I have 2 moles of gas in the products. And there's a rule that if you decrease the volume, you're going to shift to the side that has fewer moles of gas. And you can think about, well, the system's becoming more compact by going from 4 moles of gas to 2 moles of gas. Also, this 4 moles of gas is affected more by changing the volume than these guys are. So they're much more likely to bump into each other and react. Well, let's look at another. So now I have a positive change of enthalpy. So heat is going to be a reactant. Okay, and I want to know what happens if we add or remove any substance. So I've got my K expression. Whoops. There we go. Okay, I've got my K expression. I leave this out because it's a solid. And my first question is going to be, if I add ammonia. If I add ammonia, I just know that I made this number larger, my Q is bigger than my K, so I'm going to have to shift left and turn some products into reactants. As I shift left, these concentrations decrease, and the amount of my solid increases, even though the solid isn't part of the reaction. If I remove the ammonia, the opposite's going to happen. Now this number's too small. I plug in to see if I'm at K. No, I'm not, because I just made the number smaller. Q is too small, it's less than K. So I don't have enough products, I'm going to shift right. And some reactants will turn into products. So that means I'm going to increase here, here, and here to get back up to something that will give me a product equal to K. So I'm going to lose some solid. Meanwhile, if I add or remove this ammonium carbonate, I'm not changing any of these things, and this is what the equilibrium is based off of, so nothing happens. I'm still at equilibrium. No shifting, no change. Okay, same thing with adding the inert helium. I don't change these concentrations, so there's no change. And if I increase the temperature, well, now K changes. And I can see if I increase the temperature, I'm adding a reactant. There's too many reactants. I'm going to shift right. So in this case, I'm going to shift right for this endothermic reaction. And I can see that I'm going to have more products, so K increases. Next, if I decrease the volume, well, I can see I'm going to shift to the side that has fewer moles of gas. So if I decrease the volume, these gases are more likely to run into each other. Also, by decreasing the volume, I increase their concentrations. They're larger than K. I'm going to have to shift left. So I'll shift left. I'll end up making more of the solid. I'll decrease these concentrations back to their equilibrium values. And I'll be shifting to the side that has fewer moles of